Hello everyone, this is chapter 9.2 where we'll be discussing two variable linear systems. So let us first recall that a linear system is just a system of equations where the equations are linear, so there's no power on the variables. And two variable linear systems are just obviously linear systems with only two variables involved. And we'll only be looking at the case where we have two equations as well. If you have more than one equation, or more than two equations I should say, with only two variables, well, it's a little technical, but basically it suffices to only have two. If you have more than two, then it's kind of overkill, basically. Right. So now the only method we'll be seeing in this section, actually, kind of like we saw substitution in 9.1, we'll be seeing the method of elimination here. And here I say for elimination, constant multiples of equations in a system are added together so that one or more variable is cancelled or eliminated. And from there we back substitute as needed. So in particular for two variable linear system, basically what happens is you want to cancel out one of the variables so that we only have an equation of one variable and then we can solve like usual. Now, eventually I want to do this one, but for right now, let's kind of start with something a little easier. This I think is more simple. Now notice if you add these straight together, if you just add, remember our notation, this is equation 1, this is equation 2. If you add these together, what happens is the y's cancel out. So the y variable here has been eliminated. What we have left over is 2x plus 5x, which is 7x, equals 3 plus 4 is 7. So from here we can divide by 7, and we get x is equal to 1. So we have part of our solution, we just need to find y now, and we can find y by back substituting, basically. So we can plug back into any equation we want, but I'll plug back into 1. So plugging x equals 1 back into equation 1 gives us 2x, which is 2 times 1 now, plus y equals 3. So 2 plus y is equal to 3. So subtracting 2 gives us y is equal to 1 as well. So altogether our solution is 1, 1. Fantastic. Now why did I say constant multiples of equation are added? Because not all the time will you have a nice scenario like this where just adding together does the trick right away. In fact, we notice here with this problem, if you add these together, neither x nor y eliminates. In fact, if you were to multiply the top or bottom equation by any integer, you'll never get one of the other ones. For instance, if this was a 2y, then multiplying the bottom by 2 would match up with this 4y. But then the signs wouldn't be the same. So you have to make sure the signs are, well, here the signs would be the same. But we have to make sure that the signs are opposite so that when you add together, they cancel out. So you have to be a little careful. In fact, in this case, what I would do is I would multiply the top by 2 and the bottom by -3. And what that does is it'll make for x, 6x on top, -6x on the bottom, and, well, adding straight down after that, it will actually cancel these out. So what I'm going to do now is I want to do this example. So I'm going to raise some of this here, and I'm going to label this as an example, and then we'll actually go through that process right now. Right, so like I was just mentioning, in this particular instance, what I would do is I would multiply the top by 2 and the bottom by 3. In fact, it'd be -3 because otherwise the x's would be the same sign, and adding straight down would not eliminate an x. So you have to make sure that whatever you're trying to eliminate, the signs are opposite and the numbers are the same. All right, so but that doesn't mean this is the only way of doing it. Of course, if you wanted to eliminate, let's say, y, you can multiply the top by 4 and bottom by -5. And in fact, actually top by 5, bottom by -4. But in fact, that's kind of the overkill way of doing it usually. Sometimes, in this case it doesn't happen, but sometimes what you need to look for really is what is called the least common multiple of the number that is in front of x or y, so of the coefficients basically. Now in this case, 3, 2, and 4 and 5 respectively have nothing in common. So 3 and 2 have nothing in common, 4 and 5 individually have nothing in common. So with that being said, we have to basically just multiply the equations by the other one. So I know I'm going a little bit on a tangent, but just to kind of give you an idea. Let's say we had 6x on top and 10x on the bottom. We could multiply the top by 10 and bottom by 6, sure. Yeah, we get 60 is 60, and that's it. But is there a smaller solution? Of course. If you multiply top by 5 and bottom by 3, then you get 30, which is the least common multiple of 6 and 10. So that's what I was trying to say there. So just kind of bear that in mind. Now here, once we multiply, we get something a little different. So let's write a result over here. So the top equation now becomes 6x minus 8y is equal to 2, and the bottom one becomes negative 6x plus 15y is equal to negative 9. Good. Adding straight down, the x's eliminate. Great. And we get 15 minus 8, which is 7y. And here we get negative 7. So notice here, when you divide by 7, kind of similar to the previous example, coincidentally, we get y is equal to negative 1. Now we can plug this back into either equation. I'll plug it back into, I guess, equation 1, but it doesn't matter. And that's 3x minus 4y, but we know y is negative 1 now. So that's 3x plus 4 is equal to 1, just like that. Subtract 4, we get 3x is equal to 1 minus 4, which is negative 3. And then divide by 3, we get x is equal to negative 1. So the ordered pair solution here is negative 1 comma negative 1. The x value we got comma the y value we got. Great. And now I gave a different example here. Now this example is kind of funny because there are fractions, of course. So remember what we just kind of explored. You can multiply any equation by any number you want. And in fact, what better in this case than to just clear denominators? So notice if you multiply the top by, let's say, 6, that'll clear all denominators. If you multiply the bottom by 3, that'll also clear all denominators. And we get now a new system that will have the same solutions because multiplying by a number doesn't affect the solutions, as it turns out. 6 times 1/2 is 3, so that's 3x. 6 times negative 1/3 is negative 2y. And 6 times 1/6 is just 1. 3 multiplied to these just cancels the 3's, so we end up with a 5x plus y. And then 2 times 3 is 6. So now notice in this case, if we multiply the bottom by 2, then that'll actually eliminate y. So to see that, we'll have 3x minus 2y equals 1 for the top equation, hasn't changed. The bottom one now though becomes 10x plus 2y equals 12. And this is good because, well, they already have the same sign, or opposite signs I should say. So that means they cancel out right away. And we end up with 13x is equal to 13. So x is equal to 1. So far the solutions to these problems haven't been super creative, but that's kind of coincidence. And now plugging it back into, let's say, the first equation, 5 plus y is equal to 6. That means y is also 1 by back substituting into the second equation. So here the solution actually is 1 comma 1. All right, so yeah, not the most exciting solutions. But something to take away from this is, notice, we had a system of equations that involved fractions. If fractions scare you, you can always do this. Or if you want to make it easier in your eyes, however you want to see it. But here, notice, before we did this, if you weren't scared of fractions or intimidated by fractions, however you want to phrase it, and if you just look at it and add it straight down right away, these cancel out because y over 3 is the same as y over 3, and they're opposite signs already. The only thing is we have to figure out how to combine these fraction terms. So this really is 1 over 2x. So 1 over 2 plus 5 over 3 is, if you know the crisscross pattern method, that's 3 plus 10 over 6. So that's going to be 13 over 6x equals 2 over 1 plus 1 over 6 is 12 plus 1, so 13 over 6. Aha. So right away, multiplying both sides by 6 over 13 gives you x is equal to 1, and then you can go from there in a very similar fashion. So it just kind of goes to show that if you have fractions involved, you can get rid of them just by multiplying by numbers and then eliminate from there as needed. All right, so now we're going to take a look at something a little different. We'll still see some more examples that will involve elimination, but now we're going to be taking a look at categorizations of linear systems. Right, so before we categorize the types of linear systems, let's recall what can possibly happen when you have linear equations in one variable. And there's actually 3 possible outcomes. So the first possible outcome is the one we're kind of used to. Notice in this case, we subtract x to the other side, we get x is equal to 1, and that's our solution. We're used to this happening, so there's no news there, really. Here, we can try to do this, but we'll have to simplify both sides first. So we get 2x plus 3 is equal to 2x plus 2, but then this 2 and that 1 would combine to 3. And if you look at it right here at this moment in time, we have an expression is equal to itself, and that actually works for any value of x. But if you try to just move x's around to solve for x, then we get this 3 equals 3, which is weird because it's not really a solution for x, but it is definitely a true statement. So this implies that there's actually infinitely many solutions. And not only that, it actually implies that, that every real number x is a solution here. Okay. Now in this case, something kind of different happens. It's kind of similar, but not quite the same. If you move x's around, you get, instead of a true statement like we did for the second example, we actually get a false statement, which is never true, implying that there's actually no solution here. Okay, great. So now we're, I think, on an okay spot to compare to linear systems. And in particular, systems with two equations and two variables. So these are what are known as independent, dependent, and inconsistent systems. Dependent and independent are both consistent. Now, consistent means that there exists a solution. Inconsistent means that there exists no solution. So the number of solutions here are kind of mirrored from above. So there's one solution for independent, infinitely many solutions for dependent, and no solution for inconsistent. So notice the consistent ones have solutions. Independent has one, and dependent has infinitely many though. Now, how do the graphs look? Well, remember that linear systems in this case compose of two linear equations and two variables. And if you graph those, we have two lines. And recall that a system of equations has solutions that correspond to intersections of the graphs of those equations. Meaning in this case, we will have two lines that intersect at one point only. Whereas here, we have two lines that intersect actually infinitely many times. And it may be a little weird to think of, but basically what you end up having is the line overlaps itself. So both equations actually correspond to the same line, even though it may or may not look like it is at first glance. So like notice here, these both sides didn't look like they were the same at first, but it took some simplification for us to convince ourselves that they were indeed the same expression. Okay, and of course, if you have the same line over itself, it intersects itself infinitely many times. Now, inconsistent means, well, there's zero solutions, so there would be 0 points of intersection. And if you have two lines that don't intersect at all, those are known as parallel lines. Great. So now as far as the graph goes, that makes a lot of sense. But now as far as slope and y-intercept are concerned, here's what happens. In this case, the slopes are different. So let me just say slopes are not equal to each other. The y-intercept doesn't matter. Here, the y-intercept and the slope are the same. Slopes are equal. And let me say also y-intercepts are equal. Because if you have the same slope and same y-intercept, you have to be the same line. You kind of think of a slope-intercept form, y equals mx plus b. If m and b are the same, the lines are the same. Here, the slopes are equal, but the y-intercepts are not equal. Because even though they have the same slope, rise over run, they will not have the same y-intercept, otherwise they'd be the same line. So now let's take a look at a few examples of these cases. All right, so now on to these examples here. Well, we're going to try to solve each of these by elimination because, of course, it's what we learned in this section. Now, think for a moment, what do you want to eliminate, x or y? Well, it looks like x has the smaller numbers, so we can multiply the top by 2, and the x's will eliminate. But in fact, notice coincidentally that actually also happens with the y's, but when we're eliminating, we're not really focused on two variables at a time, only focus on one variable. That's a kind of key insight I can give you. Look at the variable with the smaller coefficients for each equation, and then look to see, is one a multiple of the other, or do we have like a free agent? In other words, there's no number in front. In this case, no number in front of x is good because we can multiply that equation by anything and match it with the other equation, basically. And in this case, since it's -2 in the other equation, I'll multiply by 2 to match the opposite coefficient. So now, after multiplying this 2, we end up getting 2x minus 4y is equal to 6. And below was -2x plus 4y is equal to 1. Now notice here we have, well, cancellation of x and y's, but we don't have cancellation on the other side. Now, what exactly that means isn't very obvious yet, but with a little bit of practice, we can kind of see that this tells us something right away. It tells us that we'll get 0 on one side and a non-zero number on the other side because these don't match. They don't cancel out. And 0 equals 7, like we saw from the thing I recalled previously for linear equations in one variable, this is a contradiction. In other words, there's no solution here. So in fact, that's really all you can say. In fact, one way of saying this is that your solution is the empty set. So these are equivalent statements. So that's just one way of saying there's no solution. In fact, you could actually use this just in general, not even in systems. But yes, this is an inconsistent system, speaking of which. And now moving on to the next example, inconsistent linear system. Might as well include that as a part of our answer. Of course, it depends if the question is asking what type of system. Here I didn't really specify. Now onto this one, you'll see something kind of similar. Now notice that y here is a free agent in the sense you can multiply it by anything to match the other equation. And if you multiply it by 2, you would actually match this 2 here. The only problem is that they're both negative and you wouldn't get cancellation, so be careful there. In this case, multiplying by -2 does the trick and it changes the sign to positive now. So now after making this multiplication, on the top we get -4x plus 2y equals 2, and below we had 4x minus 2y equals 2. In fact, you know what, this was -2. And now what you notice is that unlike, kind of similar, but unlike this previous example, yeah, these cancel, sure, but these also cancel on the other side. So with that being said, we get cancellation everywhere, and we get 0 equals 0, which is actually a true statement, unlike a non-true statement here. So what that tells us is that there are infinitely many solutions. Now, something I kind of specified earlier was that, well, this isn't really the answer, but we'll see right now, we'll specify. Something I kind of specified on earlier was that for the example I gave you involving one equation with one variable, there are infinitely many solutions, and I went a little further and I said any value of x works. Now you need to be careful here, because just because there are infinitely many solutions doesn't mean that every ordered pair you pick is automatically a solution. It doesn't quite work like that. What it does tell you though is that each of these has the same equation. So solution to one would automatically be a solution to the other. Now remember, that doesn't always happen in general. In general, you have to see if your solution to the system satisfies both. Just because it satisfies one doesn't mean it guarantees it'll satisfy all of the other equations in the system. But in this case it does because, well, there are infinitely many solutions, as it turns out. And in fact, the way we'll phrase that is we'll say that our solution set is the following. I guess we can call it S for solutions. We don't even have to call it anything, but I'll call it S. So our solution set S is the set of all ordered pairs x comma y such that it satisfies one of these. And in fact, if we look at the top one here, before multiplying by -2, if we isolated y, you can actually swap these. So subtract 1 and add y to the other side. We'll get y is equal to 2x minus 1. So let me say such that y is equal to 2x minus 1. There are probably other ways of phrasing this, but basically what this says is that every solution to the system would look like this. So just to give you some little examples, let's let y equal 1. Or we can let y equal 0. When y is equal to 0, I'm sorry, we want to let x equal 0. When we let x equal 0, what's y? It'll be -1. So 0 comma -1 is in the set. So if you want, we can write it like this. So that's in the set. If you want to plug in +1 for x, you'll get 1 comma, let's see, 2 minus 1 is 1. If you want to plug in, let's say, -1, we get -2 minus 1, that's going to be -3, and so on. And in fact, you don't have to plug in integers. You can actually plug in any number, like 1/2 or radical 2. So really what this says is that your solutions will look like this. They're the set of all ordered pairs where the y value is 2x minus 1. Kind of interesting. So not only can we just say that there are infinitely many solutions, but we actually know what the solutions look like. But again, there's infinitely many of these ordered pairs x, y. And here's just a list of a few of them. Now, as far as the type of system this was a dependent system, and it's consistent because there exist solutions. So dependent and consistent. And by the way, the reason why it's called dependent is because one of the variables depends on the other one. Notice here, y is written in terms of x. So there's some dependency going on there. And usually that doesn't happen. Usually x and y are independent of each other, in the sense you can't write one in terms of the other for all values of x in this case. All right, so honestly that really concludes 9.2. That's really all I wanted to discuss. Elimination, types of linear systems, and that's really it. So now we're going to move on to 9.3 in the next video, where we'll be discussing multivariable systems. And it's going to be a little wild, but we'll look forward to that, and I'll see you in the next video for that. Thanks for watching. See you then.